All right, let's go over a few example problems that might be like what you would see on your upcoming exam. I can't guarantee that the types of problems we see here will cover absolutely everything that's on it, right? It's still anything from chapters 6 through 10 is fair game, but these examples that we'll do here shortly will be a very good representative sample of the types of problems, like the difficulty level that you might see. So if you're only going to study one thing, it would be this review. But yeah, make sure you also go over the other material that we don't cover here, right? Okay, so let's start with a couple examples then. Let's see. Let's say, so we have for one here, we can say children in a treehouse lift up a small dog in a basket, and they're going to lift it 3.85 meters up. So it's actually kind of a tall treehouse, like 12 or 13 feet high. So we're going to say if it takes 201 joules of work to do this, what is the mass of the dog and the basket together, right? So we've got some kids in their treehouse or whatever. We're going to have a little dog in a basket, and it's going to be lifted up some distance, right? It's going to go up 3.85 meters. And what we know is the total amount of work that it takes to do that. So we don't know the details of, exactly how hard are they pulling on this. Are they, pulling it up really quickly? Are they kind of slowly dragging it up or anything like that? But it doesn't really matter, right? So what we want to do is we want to find the mass of the dog and the basket together. We know that they are working against gravity, right? So gravity, there's some sort of force that they are applying up. Gravity, so the applied force, and there's some sort of gravitational force, right? mg pulling down on this dog and basket. And we know that um, over the course of this distance, this gravity will do some sort of work on this, right? And so the work that they have to do, this 201 joules, that must be enough work to actually overcome the gravity over this distance. So we don't know all the exact details of exactly how this dog and this basket are getting up there. We know they're being pulled up in some way, but as far as how long does it take them or anything like that, we're not sure. But again, we know what the total amount of work that they need to do to get them this distance is, right? And so with that, we can just very simply write um, our standard equation for work, right? That the work that they do, 201 joules, is going to be F times D, right? And so in this case, we don't have to worry about the cosine. We're just pulling it straight up. Gravity's pulling it straight down. So the applied force is up. The displacement is up, right? We don't have any information about this. They're not pulling it up at an angle or anything like that, right? So we just have work equals F dot D. This, of course, is um, m times g times d, right? So we don't know the mass, we do know gravity, we do know the distance, and we do know the work. So we can simply solve for this m. If we do that, what we get is something that looks like this. We have 201 joules of work divided by 9.8 meters per second squared times 3.85 meters. And so the mass of the dog and the basket is about 5.3 kilograms, right? So again, there's a lot of details that we don't know about exactly how they're doing this. Maybe they're slowly pulling it up, or maybe they're very quickly pulling it up. But again, it doesn't matter. We know what the total amount of work that was done um, by these kids as they're pulling this up must be, and therefore we can figure out what the mass of this is just using our very simple work equals F dot D formula that we have here. Okay, so yeah, just a quick review of our work stuff. So along with that, of course, we have the other application of this kind of work and energy stuff we have is conservation of energy. So let's do one of those. So in this case, we're going to say we have a 1.4 kilogram block, slides without friction at 0.95 meters per second on a horizontal surface until it encounters a spring with a spring constant of 735 newtons per meter. And so then what we want to know is how fast is the block moving after compressing the spring by 2 centimeters. That's what we're saying here. So we have our block. It's moving initially with some speed, we'll say v1, right? And then it's moving towards some sort of spring, right? That's attached, I don't know, in some way or another, right? It's like sliding along this tail or something like that. It's going to run into this spring and it's going to compress it. So this is kind of our before picture. Then our after picture, right? We have this block is now compressed this spring a distance of 2 centimeters, and it's still moving, right? We're not saying that it's come to a rest yet. We are saying that our block will have some sort of speed it's still moving with, right? Still, it's obviously it's going to compress this spring. It's going to start to slow down, um, but we're saying how fast is it moving after it's compressed the spring by 2 centimeters. So again, conceptually, we have only conservative forces acting, right? We have a nice frictionless surface here, so we have gravity pulling down, normal force going up. Those will cancel out. We don't need to worry about that. And then, of course, once we start interacting with this spring, we do have the spring force pushing back, right? So essentially what we're doing is we have kinetic energy in the block, and we're going to convert it into potential energy as we squeeze this spring and compress it more and more, right? So initially, what do we start with? This is a very basic conservation of mechanical energy. So we just have what we have 1/2 m v1 squared, right? We're given what our initial speed is, 0.95 meters per second. So this is our total initial mechanical energy, right? This is not compressed at all, so there's no mechanical energy stored in there. We don't have to worry about gravitational potential energy again because we're not moving up or down, so we can set it to whatever we want and it'll just be constant and it'll cancel out. So we want to have mv squared equals, now we are going to compress this a little bit, right? But we are still moving, so we still have 1/2 mv2 squared, right? So we've slowed down some amount, and what we lost in this kinetic energy, we gained in spring potential energy, right? The more you squeeze this spring, the more potential energy you are storing in the spring itself, right? So it'll look something like this, right? So we have the mass of our block, right, 1.4 kilograms. We have the initial speed of our block. We have the mass of our block again. We don't have this second speed. That's what we're looking for, so it's good that that shows up. We have K, right? We have the spring constant, how stiff our spring is, 735 newtons per meter. And we know that this spring has now been compressed by 2 centimeters, right? So we can solve for our final velocity, right? Our V2, it'll look like this. We have V2 equals, here we can cancel out all my 1/2s. We can't cancel out the m's. It's the square root of v1 squared minus kx squared divided by m, right? And so then if we do this, if we plug everything in, our speed that we get after is about 0.83 meters per second, right? So we have started to slow down. We're still going to compress this in a little bit more, right? At some point, we'll end up at 0. Then, of course, if it really is frictionless, it's not going to just stay in place. It'll actually push it back out. It'll leave with the exact same speed that it came in with, or it'll just come in, bounce off, and then go back out. But we're not interested in the whole picture of exactly what's going to happen. We just want to know after it's compressed at this initial 2 centimeters that we have slowed down. We are now moving at about 0.83 meters per second, right? Okay. All right, so we've got our conservation of energy. We've got some of our work problems that we have. We can also now, let's go on ahead. Let's do some torque problems that we've seen before, right? So I'll just do a basic one here, just kind of balancing out a very simple statics problem that we have. So here we're going to say we have 2 kids push on opposite sides of a door. We're going to say then one is pushing with a force of 17.5 newtons at a distance of 0.6 meters away from the hinges. So what we want to know is if the second kid is pushing at 0.45 meters away from the hinges, then with what force must they push, right? The second kid, with what force must they push in order to keep the door from moving? So again, we'll draw our picture. We have something that looks like this. So if I'm looking at the door from above, right, I'm looking down on the door here. Here are the hinges here on the left side as I have it drawn. We don't know exactly how long the door is, but we're going to say, we have one kid who's pushing here. We have F1 at a distance R1, and then we have another kid who is pushing at a distance R2 with F2, right? So we have one that's pushing at, I didn't quite draw this to scale, but that's all right. So we're going to say we have F1 is the one we know everything about, 17.5 newtons. So R1 is 0.6 meters, R2 is 0.45 meters, and then F2 is what we don't know, right? F2 is what we want to find. So just basically, again, our basic statics problem that we have, both of these will apply a torque. And so if we balance out these 2 torques here, we can see that this door will not be rotating. Then, of course, we can assume pretty safely, right, that the door is also not going to move. The hinges will be strong enough to hold our door in place. We're not going to worry about balancing out the forces. Obviously, these two forces are not equal, right? They're not going to be equal. They have to be different in order to have the torques balance out. Um, but then, of course, the difference in this force will be more than made up for by the hinge, which is kind of just holding this door in place, right? So we're not going to worry about balancing out forces. I know, strictly speaking, you would have to say net force is equal to 0 and net torque is equal to 0. If you did that, all you would find is whatever force this hinge is exerting in order to keep the door from moving. But we're just going to take it for granted that the hinge is strong enough to not break from two little kids playing on this door, right? So yeah, so let's see what we have to do then. So we have our two different torques would be this, right? So this one is trying to spin it counterclockwise. This one's trying to spin it clockwise. So we set our clockwise torques equal to our counterclockwise torques to balance them out. So we have R1, F1 equals R2, F2, right? And just very simple. It's basically the same problem mathematically as when we had the kids on the seesaw or whatever, right? We just have two different forces that we're trying to balance out. They're the torques that are applied by each of them. So in this case, it's very simple. F2 must be R1 over R2 times F1. This, of course, is 0.6 meters divided by 0.45 meters times 17.5 newtons. And what you get is a force of 23.3 newtons, right? So maybe they're like playing tag or something, and one of them's trying to cheat and close the door on the other one or something like that. So that in order to keep this door closed, if they're pushing here in this way, then if one of them is pushing with 17.5 newtons and the other one's pushing with 23.3 newtons, and they're pushing at these different spots, these different distances away from the hinge, then the door will neither open nor close. It'll just kind of stay as it is, just like this. We'll have our torques balanced out and we'll be in static equilibrium. Okay. We'll do one more, and we'll kind of do a new type of problem that we haven't quite done before. It's somewhat similar to the other stuff that we've seen in the past, though, with our conservation of angular momentum. But in this case, we are going to have essentially what is an angular momentum collision, right? So we're going to have it works very similarly to momentum collisions that we've seen before, but now in this case we are going to conserve angular momentum, right? So we have done that before, so that's kind of what's familiar to us. It's just kind of the overall setup that might be a little bit trickier at first. So let's see what we have. So in this case, we're going to say we have a merry-go-round has a mass of 120 kilograms and a radius of 1.8 meters. It's going to be rotating at 0.5 revolutions per second. So this isn't in radians per second, it's in revolutions per second. That's okay, as long as we keep it in that, we can find our final answer in that, and it doesn't really matter which units we work in. Just make sure you keep track of which units, make sure you know what units you're using, right? Don't just put numbers in. So we have our omega, right, our angular velocity of 0.5 revolutions per second. Then we're going to say a child with a mass of 22 kilograms is standing still next to it, right? So they're not on it, but they're standing still next to it. And then they are going to grab on to the edge of this merry-go-round. So when that happens, that's essentially going to be an angular momentum collision, right? You can think of it as like an inelastic angular momentum collision in some sense, where the angular momentum is going to be conserved, right? But we have to figure out exactly how that's going to change what's going on. So we're going to say, what is the new omega of the merry-go-round and child together? So let's draw our picture out here. So we have some sort of merry-go-round, looks like this. It has some sort of radius, has some sort of mass, and it is spinning with some omega, right? It's moving at half a revolution per second, so it's actually going pretty quickly. So there's some kid standing right here, right? We're going to say with a mass of little m, and then we're going to say afterwards they are going to grab on to the edge of this merry-go-round. So nothing else about the merry-go-round has changed. It's still the same size, it's still the same mass, but we will have a different omega, right? So what else about this picture has changed now, right? So as you can imagine, right, if this person was standing still and they grab on, it will affect how this merry-go-round is spinning, right? So essentially what we're doing is when we do this, we're kind of changing the, again, it's another way that we can think of changing the rotational inertia of the merry-go-round, right? Now we don't just have the disk of the merry-go-round itself, we have the whole system of the merry-go-round plus the person. So we'll have a new rotational inertia. We'll have a new value of I that we have to use to calculate what this omega is going to be. So yeah, so this is our before and after. So we can write our equations for that, right? We're going to conserve our angular momentum. There are no excuse me. All right, sorry about that. So yeah, so there are no external torques or anything like that acting on the system. So we are going to conserve our angular momentum. So we know that it's going to look like this. We're going to have I omega equals I prime omega prime, right? So in this case, essentially how I'm doing this, you can think of it in two different ways. The way I'm doing it is this is one system, right? Or this is kind of one object where initially this person is contributing no angular momentum, right? They are not moving. Their v is 0, right? So they can't have any sort of omega at all. And so then when this person latches on to the merry-go-round, I'm going to say that we are essentially just effectively changing the moment of inertia, sorry, the rotational inertia of the merry-go-round itself, right? So that's going to change. We're going to have a different I, and we're going to have a different omega, right? So the I is increasing, so you would expect that the omega will decrease, which makes sense, right? Okay, so what is our initial rotational inertia? We have 1/2 mr squared times omega equals, what is our new, afterwards we have a new rotational inertia, which is 1/2 mr squared plus mr squared times omega prime. So this person has it grabbed onto the edge of the merry-go-round, so they are at the edge of it, right? So their distance away from our rotational axis would just be the same distance as the radius of the merry-go-round, right? So this disc shape is basically the same as a cylinder. So our rotational inertia is going to be 1/2 mr squared. If you again, I'll give you this on the exam if you need it. So that's where this one comes from. They will be both moving together right, at the same omega since they've grabbed onto this. And so this is what our conservation of angular momentum equation would look like. So with this, we can then solve for our omega prime, right? And so this is just going to be 1/2 m r squared times omega divided by 1/2 m r squared plus m r squared. And actually, the r's will all cancel out. And what we will get for our new omega, right, our new angular velocity, will be 0.37 revolutions per second. So it does look very similar to the other types of problems that we've seen with our conservation of angular momentum before. One little trick one thing I could switch up about this to kind of change this problem is I could say maybe my initial case looks more like this, where I have my merry-go-round is spinning, and then someone, say, runs along there and grabs that, right? So how would you go about doing that one? Well, of course, they would have some V. When they grab onto it, they would have some R, right? And this, again, is a kind of an easier way to see why I'm kind of calling this an angular momentum collision, right? In some sense, you have the merry-go-round is spinning. You have the person is running around. They're not really running around. Maybe they are running around. Maybe they're just running tangentially to it. But when they grab on, right, in that instant that they grab on, they do have some v, right? They do have some distance away, and so you can say that they do have an angular momentum initially before they got on. So then you'd have to have another term up here, right? You'd have initial angular momentum for both the merry-go-round and the person running along, right? And then, of course, the after picture would still be kind of analogous to our inelastic collisions where this person jumps on the merry-go-round initially, right? Or sorry, jumps on the merry-go-round afterwards. So that would just be kind of another way that you could kind of phrase this problem, right? So I did kind of the simpler case where this person was standing still and then hops on. But if you were going to if I were going to maybe ask this on the exam, I don't know. Why would I be going into this much detail? If you were going to have someone running along here and jumping on, this is how you would do it, right? You have a V and you have an R. That gives you your omega, and then their rotational inertia would just be that of a point mass, right? So that would add on an extra term to your initial angular momentum that you'd have there, which could then change the after picture, right? After these two have quote unquote collided and stuck together. So yeah, so that's just kind of four pretty good problems that I that will be similar to stuff that I will ask you on the exam. Again, that doesn't cover everything. There's other stuff from chapter 6, especially, I think, that we didn't quite cover much of here. Make sure you still know what the centripetal force is. We do have some, I'll have some sort of simple momentum collision problem, right? Conservation momentum problem. We'll also have some sort of conservation of angular momentum problem. I went over this one, right? We've done more of the momentum examples in the past. But yeah, so again, anything from chapter 6 through 10 is fair game. So this will cover most of it, this review that we just did here quickly. But yeah, make sure you study all of the material for the upcoming exam.